Okay, so this is the summary of where we are. We've been studying time translations. We've learned we can implement time translations on our state or on our operator. Taking the initial state and multiplying by u of t, we get the state at time t. Taking the initial operator and then computing u dagger operator u, we get the operator at time t. So we know how to implement time translations either on the state, as in the Schrödinger picture, or on the operator, as in the Heisenberg picture. And the unitary operator that implements time translations is nothing but e to the minus I ht over h bar. What I want to do now is, so now I want to study spatial translations. So how do I translate in space? Okay. Here is my basic claim, and then I'm going to try to justify this claim to you. A spatial translation by some distance a along the x direction is just given by e to the I ap over h bar. So notice that a space translation looks exactly like a time translation. The only difference is the sign in the exponential. Okay, so how do we prove this? Well, we can take e to the I ap over h bar. We can apply it to our state, and then we can project to position space. So that's exactly what I've written down there. And with just a little bit of manipulations that are hopefully familiar to you, using bras and kets, you can rearrange this and obtain the following expression. E to the a d by dx onto psi of x. So let me just maybe say one thing that is hopefully useful to you. I want you to remember that probably you are used to translating the momentum operator into position space as minus I h bar d by dx. So this is how you would translate the position operator into momentum space. So hopefully that formula looks quite reasonable to you. Now we've got an exponential of the derivative. How should we understand that? Well, whenever you have a function of the operator, you understand it in terms of the power series expansion for that function. For the exponential e to the x, you know exactly what the power series expansion is. The exponential e to the x is just the sum from n is equal to 0 to infinity of x to the n over n factorial. So if we've got the exponential of a d by dx, how should we understand that? Well, I'm going to use this power series formula for the exponential. So term with n is equal to 0 is just a 1. So I'll just have 1 plus the first order term with n is 1. Well, I need to take a d by dx, raise it to the power of 1, divide by 1 factorial. Then plus, I should square a d by dx. So this will give me a squared d2 dx2. I should divide by 2 factorial. And let's write in just one more term, just to make sure that things are completely clear. And then it would continue. The power series expansion continues to infinity, and we would get psi of x. And if we work out what this is just psi of x plus a d psi dx plus a squared over 2 factorial d2 psi dx2, and so it keeps going. Now, the next thing that's important to do, let's recognize this last expression that I've put in the green box over here. If we want to recognize that expression, what is it? Okay, well, this is equal to, so let's say green box is equal to It is the infinite order Taylor expansion of psi of x plus a. So if you just take psi of x plus a and you expand in a, you'll get precisely the Taylor expansion that you see sitting over there. So the sum of the green box is the psi of x plus a. So what did we prove? We have proved that if you project e to the I AP over h bar acting onto psi into position space, you just get the psi of x plus a. So as advertised, this exponential operator is performing a translation in space. Okay. Now I'd like to combine the spatial translation with the time translation that we've already considered. So I want to translate in time by a naught and in space by a, i.e., I want to translate by a mu, which is a naught, comma a. So I'm translating in time and space. So let's write down that operator. So I want the u of a mu, okay? I'll often just call this the u of a, so I often won't indicate that space-time index. And this is just given by the exponential of, now, remember for time translations, we had e to the minus I ht over h bar. So here we'll have minus I a naught times the Hamiltonian over h bar. That's the rule for translating in time. And then the rule for translating in space, all that we do is change the sign. So we'll have I vector A dotted into vector P over h bar. So that's u of A. And how can we write this? Well, we've already got the 4 vector A mu. We can also introduce the 4 vector P mu, which is the Hamiltonian and the momentum operator. And then take a look here. We've got what looks like A naught P naught minus A dot P appearing. So indeed, this can be just written very nicely as minus I A mu P mu over H bar. And as usual, I'm going to set H bar to 1. And I'm just going to write this as E to the minus I A dot P. So that's the rule that I wanted. U of A is equal to E to the minus I A dot P. And U of A will perform a translation in space and time. Good. So now we're ready to write down our third axiom, A3. So how do we translate an operator? Well, we need U dagger, the operator U. So let's take U dagger of A, our operator, which is phi of x, and then U of A. And this will be the phi of x plus A. And let's just write this out explicitly. If U is e to the minus IAP, then U dagger of A will be equal to, we'll have E. We need to complex conjugate the minus I, which will give us a plus I. We need to complex conjugate A, but that's real, so it stays the same. And we need to take the dagger of the 4 vector P mu. But P mu has the Hamiltonian, the momentum operators in it. That's all Hermitian. So P dagger is equal to P. Okay? P mu dagger is just P mu. So U dagger of A is e to the IAP. So using that over here, we've got e to the I A dot P phi of x e to the minus I A dot P. And this axiom A3 is telling us exactly how our field forms under translations in space-time.